Right, so we get to a couple of regularity tools now, as I call them, in this lecture and the next. Two lemmas. One is called the counting lemma, and we'll do that today, and the other is going to be the removal lemma. And those are standard tools nowadays that emerged a little later than the regularity lemma itself, and they basically implement techniques that we've seen already, especially in the proof of the blow-up lemma and the two applications that we have seen. So formally, we need a slightly different notion of regularity, which I call uniformity. That's just to keep the two things apart for the purpose of this lecture course and in the book. Normally both are called regularity, and people then just have to say which version of regularity they use. So we call it uniformity. So a pair of disjoint vertex sets is epsilon d uniform, where d is you can think of d as a target density. For example, the density of the entire pair AB in the graph G. If this inequality there is satisfied, now how does that differ from the requirement for regularity, for epsilon regularity? There are two differences. One is that this requirement here, that the density of every subset X of A and Y of B has to be close to the overall density between A and B, where close is measured by epsilon. This is now required of all subsets X and Y. So no longer of sets X and Y that have a certain minimum size, like epsilon order A or epsilon order B. Even smaller subsets X and Y have to satisfy this now, but what they have to satisfy is a little weaker. The difference between the number of edges between X and Y and d time and the number of and d times the number of possible edges, d times order X order Y. This difference is bounded above by epsilon times order A order B rather than order X order Y. Okay? And you can rewrite that, as you can see it here, by dividing this term by order X order Y. And then you get the difference between the densities themselves on the left. So the density between X and Y should differ from the overall density D, which is the parameter given there in the definition, but you can think of it as the density of AB, by at most epsilon times something. It used to be epsilon, right? The densities should differ by no more than epsilon, density between X and Y, and density between A and B should differ by no more than epsilon. But now we relax that and we allow the upper bound to be multiplied by a factor that is bigger than 1. So the factor is order A, order B, divided by order X, order Y. Right? Order X, order Y is smaller than AB. So that is bigger than 1. So if you like, for small sets, so the smaller X and Y are, the less we ask of this inequality. The less we ask about the comparison of the densities between X, Y, and AB. But we're not exempting X and Y altogether when they're too small. Okay, so this density parameter D can be written into the definition, and we sometimes fix it, but usually it'll be just D of AB. Okay, and when it is, we just speak of epsilon uniformity rather than epsilon comma d uniformity. And we have this implication that when a pair is epsilon regular, it's also epsilon uniform. Well, that's not, it's easy, but not entirely trivial. The inequality is weaker now, but we're asking it for more sets. So you have to here prove that the uniformity inequality applies also for small subsets x and y, assuming epsilon regularity. That doesn't ask anything of small subsets, but you can prove that. And then when you're epsilon uniform, you're also cubic root of epsilon regular. So regularity and uniformity, as we call them here, are qualitatively the same within a constant factor, depending, well, cubic root of epsilon is the factor, right? Okay, so in what follows, we will technically assume epsilon uniformity, but when I speak of assumptions that we're making, I quite deliberately assume epsilon regularity, bearing in mind that it is stronger, that it implies epsilon uniformity. So when I say or write epsilon regular, I mean it. Okay, and when I really want to mean and use the uniformity definition, as in the statement of the counting lemma later, then it'll be there explicitly. Okay, questions about the definition? No. Okay. Right, so on to the counting lemma. What does the counting lemma do? It assumes that we have a graph that comes with a epsilon regular partition, V0, V1 up to Vk. And these pairs will have certain densities, and we'll be talking about those. So we're assuming that some epsilon regular partition or epsilon uniform partition is given when we consider a graph G. And we'll be counting, that's what the counting lemma does, we'll be counting essentially copies of a given graph H in G. Right, so we're asking, as we did in the blow-up lemma, which graphs H can be embedded in G. And under what assumptions can H be embedded in G, and so on. That's what we'll be asking. And technically, we'll be speaking about homomorphisms from H to G. So what's a homomorphism from a graph H to a graph G? That's a map from the vertices to the vertices that preserves adjacency. It doesn't need to preserve non-adjacency. And it doesn't have to be injective. Right, so once more, a homomorphism from H to G is a map from the vertices of H to the vertices of G, not necessarily injective, or surjective, such that any pair of adjacent vertices here are mapped to adjacent vertices there, and in particular not to the same vertex. Right? So this is normally hidden when you read in the literature the definition of homomorphism. It always glosses over this fact that it's meant to imply that adjacent vertices cannot map to the same vertex because the same vertex isn't adjacent to itself. Right? And it never is in our context because we don't have loops. If there was a loop, it would be allowed, and in some contexts that is considered, but we don't have loops. Okay, so that's what homomorphisms are. And injective homomorphisms give you copies of H in G, right, as subgraphs, not induced subgraphs, but subgraphs. H is mapped injectively, vertices are mapped injectively to vertices of G, so that adjacency is preserved. So we get an image of H, a copy of H as the image, as a subgraph of G. And we'd be counting those homomorphisms from a fixed copy of H to some varying big graphs G. And as in the proof of the blow-up lemma, we fix target partition classes for the vertices of H. So remember that when G has these partition classes, and our G's always come with an epsilon regular partition, then H should map to G in such a way that the vertices are mapped to partition classes that we specify in advance. Right? In the proof of the blow-up lemma, these vertices were sitting in classes too, these classes of S vertices of RS. And then the target class was the copy or the corresponding class in the partition. Now we just have any specification for every vertex of H. We assign it a little index between 1 and k that signifies the target class to which it should be mapped. Okay. And we're counting homomorphisms from H to G that respect this assignment of target classes. Okay, so here's a bunch of definitions, just notation. Hom Hg, big H, is the set of homomorphisms from H to G. Hom little phi of Hg is the set of homomorphisms that observe or respect this assignment of partition classes. Right? This phi is not the homomorphism itself. This phi is just a map that assigns to every vertex of H a little index I, little I, between 1 and k, telling us which class to map this vertex to. So little phi is not the homomorphism. But the set of all homomorphisms from big H to big G that respect this assignment of partition classes, little phi, that is denoted as big hom index phi of Hg. And with little h's, hom Hg and hom phi Hg, that's just the number of those homomorphisms respectively. Okay? And the counting lemma, very roughly, tells us that the number of homomorphisms from H to G that respect a particular given phi, we give ourselves any phi, little phi, that assigns partition classes, then we count the number of homomorphisms that respect that. So little hom phi of Hg, that is roughly the expected number of homomorphisms we would get if G was a random k-partite graph, which with edge probabilities, the densities between the classes. Right, so G comes with this epsilon regular partition. We're assuming that all these pairs of classes are epsilon regular. Maybe G has many more partition classes. We're just looking at some of them, which we target by our little phi. So there may be more. But those that we're looking at, we're assuming that all pairs are epsilon regular. Okay, and then they have different densities. Some are dense pairs, some are not so dense pairs. That's fine. The densities are denoted, for example, by dij, where this is vi and this is vj. All right, so those are the densities. And if we now chose the edges between these vertex classes, suppose there weren't any edges there, we just knew these densities, and then we would choose edges uniformly at random, independently of each other, with probability dij between these two classes. Then we'd expect to get this density, right? The number of actual edges divided by the number of possible edges. And the number of homomorphisms respecting little phi from H to G is the expected number of homomorphisms that we would get if we mapped the vertices of H to the designated classes at random, and then just checked whether this random map happens to be a homomorphism or not. Okay, and we'll find that this number is constant times order h to the power of order g to the power of order h, which goes to infinity when g gets large. So c constant times g to the power of h. So that gets large as g gets large. And so there's going to be lots of homomorphisms. And often we'll just be interested in asking whether there's at least one, right? So we'll look at that more closely in a moment. Okay, in particular, this constant c that depends on h, which we consider as fixed, on the epsilon we choose, or not choose, the epsilon that is the basis for this epsilon regular partition, and the actual densities dij. That's what the constant c depends on. So in particular, if all these densities are bigger than 0, then this constant will also be bigger than 0. So this will indeed go to infinity as g grows. Okay, so let's see the formal statement of a particularly simple case of the counting lemma, and that is when H is a complete graph. Okay, so when H is a kk, little k, just by way of example, when H is a kk, then there's only one phi that can give us copies of H in G, and that is, or not one phi, but one type of phi. It must map the vertices of H to different pairwise distinct classes, right? All the vertices must come to sit in different classes. We can't have two vertices mapped to the same class because there's no edge here. Right? We're not assuming that there is any edge there. We can't count the number of copies of H that do that because we have no knowledge or assumption about any edges there. So the bipartitions, the bijections between the vertex set of H and the index set of the vertex classes here are going to be the little phi's. Okay, and then let's look at that statement. Here, the second big product, the product of all the orders of the vertex classes, order V1 times order V2 times order V3 and so on, the product of the orders of Vi for I from 1 to k, that is just the number of ways in which we can embed H injectively to these classes. Right? For every little vertex gets mapped to one class. So such a map comes from choosing vertex in V1, choosing a vertex in V2, choosing a vertex in V3, and so on, and so on. And the number of ways of doing that is order V1 times order V2 times order V3, and so on. So I'm now counting subgraphs isomorphic to KK in here. I'm not counting homomorphisms that come from permuting the vertices here and thereby mapping different vertices of H to V1, say. We're not counting those right now. We will be counting those later. So here, let's just count the subgraphs, the complete subgraphs of order K in G. And we get those by choosing one vertex from each class. Otherwise, we couldn't get a complete subgraph because the classes may be empty. And then the probability that such a particular choice of one vertex from each class is, in fact, a complete graph in G. What's that probability? Well, we have to look at all the pairs of vertices and see with what probability these, the chosen pair, is in fact an edge. Right? And if this probability is Dij, then these pairs exist for the chosen vertices, each independently with probability Dij for the respective pair Ij. So the probability that they're all there is the product of all these Dijs. Okay, so once we have fixed a choice of one vertex from each class, the probability that this choice of vertex induces a KK is the product of all the Dij, if the Dij are indeed the edge probabilities for the pair Vi, Vj. Now, we're not talking about probabilities, and we're not in a random graph here. We're, in fact, in our particular graph G, where these Dijs are not edge probabilities, but densities. I'm just saying that this term that you can see here, the product of the two big products, would be, if we were in a random scenario, the expected number of copies of the KK in G. Right? The number of ways of choosing the vertices times the probability for every such choice that it is in fact a KK. Okay, and this proposition, corollary of the counting lemma, says that the number of KKs that we actually have in this non-random concrete G with these edge densities differs from this expected number if it were a random graph by only a little bit. And what's the little bit? Well, as always, the little bit is epsilon times the obvious reference quantity, The reference quantity is the product of all the sizes of the classes Vi. So the ways of choosing, the number of ways of picking one vertex from each class. So it's epsilon that, except that you can see this other little factor, k choose 2 there. That's an annoying little thing. And it has no real function. It shouldn't be there. The reason it is there is that the corresponding little annoying factor from the real counting lemma, of which is a corollary, has a technical role in the proof. Right? It relaxes this a little bit. It makes this statement a little weaker. We don't really mind because k choose 2 is a constant. We can think of it as a constant even when we're allowed to use the regularity lemma on input epsilon to get our regular partition for G, because the number of partition classes is always bounded by this big M that depends only on epsilon and not on the G that you're actually partitioning. Right, so this is an annoying but irrelevant little constant factor, k choose 2 there, which you're very welcome to ignore until such a time as we need it in the proof of the counting lemma. Yeah. Questions about this corollary? Just the statement. I'm not asking you to see that this is true. Just about the statement. Right, it counts the number of complete K subgraphs, KKs, in G, not the number of homomorphisms, because there are more homomorphisms than images. Every concrete image of H, in particular of a complete H, can arise from several homomorphisms. We can permute the vertices of H and then send them over, or send them over in many ways. So we have k factorial ways of doing that, and that factor k factorial is not coming into play. We're just counting the subgraphs at the moment. And the proposition says that the number of these subgraphs H, complete subgraphs H, differs from the expected number of subgraphs by only a little bit. Right. Okay, on to the real counting lemma. There we are. Now, we start with phi. H is a given graph, and we're also giving ourselves a phi that assigns to every vertex of H an index between I and K. And on this index set, we're now assuming that there's a graph called big R, much like the regularity graph that we had. That's why I call it big R. So phi maps the vertices of H to the set one to K, but this is the vertex set of a particular graph R, which may have some edges but not other edges. Right? It's some graph that is, we also assume as given. And this little phi fixes target classes, and now we're asking that phi is a homomorphism from H to R. So we don't choose any old partition classes. We choose partition classes so that a pair of adjacent vertices of H gets mapped to two partition classes that make an edge in R. I'm not telling you how the edges of R come about, whether they correspond to dense pairs or something that can come later. For our purposes now, R is just a graph that has certain edges, and we're requiring of this index map that pre-assigns classes to the vertices of H, that adjacent vertices get mapped to two classes whose indices form an edge in the graph R. So it is allowed that two vertices map to the same index, but since that index is a vertex of R that doesn't have a loop, these two vertices mapping to the same index, to the same vertex of R, were then not allowed to be adjacent. Okay? But that's the only thing to bear in mind. Otherwise, this map does not have to be injective. Just bear in mind that only non-adjacent pairs of vertices can map to the same vertex of R. Okay, that's the little phi that we have given. And now, let's look at the statement. So G, as before, comes with a partition V1 to Vk, where the pairs have certain densities called Dij, and we're assuming that this is an epsilon uniform partition, an epsilon comma Dij uniform pairs. For every ij, the pair Vi, Vj has to be epsilon Dij uniform for one particular epsilon bigger than 0. That's the same for all these pairs. Now the statement says that the number of homomorphisms, little hom phi, those that respect this little phi from H to G, differs from a certain product, similar to the product we just had in the corollary, by only a little bit. What is the little bit? The little bit is epsilon times the reference quantity. Reference quantity now is the product of all these classes that appear as image classes under phi. Right? The product over all the little u in H, the vertices little u in H, take their classes and multiply the sizes of those classes. And we do this for the vertex set of H as considered as a family, right? So, or rather as the collection of these classes, the image classes as a family, indexed by the little u's that are vertices of H. So when two little u's map to the same class, then in this product, the order of that class appears twice. Right? This product has as many factors as H has vertices. So that's the reference quantity, and epsilon that is an upper bound for how close the number of phi respecting homomorphisms from H to G should be to something like their expected number, which we'll get to in a moment. Except that there is again this nasty, annoying little constant factor. This time it's the size of H, so the number of edges of H. Okay, so that's again there. And we'll later in the proof do induction on the number of edges of H. And that's where we need this factor. And that's the only reason. It facilitates the proof. Okay, so let's look at the product of the two big products from which the number of homomorphisms has to differ only a little bit. That's the same again. The right product is again the number of ways in which we can choose images for the little vertices u, for the vertices little u of h. So for every vertex little u of h, we know which class it has to go to, namely v index phi of u. And how many choices do we have for that vertex to embed that vertex? Well, the order of that class. And that's how this comes about. And we have to embed every little u. So for every little u, we have this number of choices. So that's the right product here over all the sizes of the partition classes that appear as images under phi of vertices of h. Again, counting any given class as often as it is the image class for vertices in H, even if there are many vertices mapping to that. All these vertices have to be non-adjacent in H then, right? Okay, that's the same reference quantity as this here. Same that we had before. And now we do the same as earlier in the corollary. For every such choice of one vertex, of embedding a vertex of little h in its correct class, we can see whether that particular choice defines a homomorphism or not. And the probability that this happens for a particular choice is the product over all the edges of H that the corresponding pair of classes, that the corresponding pair of images in these classes is an edge of G. And if we view the edge densities here as probabilities, then the probability of having a fixed vertex here and a fixed vertex there, that this is actually an edge, will be Dij. So much as before, this difference here that has to be small is the difference between the number of homomorphisms that we actually have from H to G, all respecting little phi, and the number of expected homomorphisms if this were a random scenario, which it isn't. But this is how these quantities come about. So as a typical application, we would show that there are many such homomorphisms. Those that respect phi are going to be called phi-partite homomorphisms. That's just a word. And we'll always be counting those. And we want to show that there are many such things. For example, at least one. That's an important special case. Right, the uniformity lemma itself, the counting lemma itself just says that the number of homomorphisms, phi-partite homomorphisms from H to G, differs from something only a little bit. So how can we hope to show that there are many? Well, by saying that the thing from which it differs only a little bit is big. Okay, and that's what we're going to do. So on this vertical axis, we have the target for the number of homomorphisms. That's the big product, right? In the term up there, in this, from which hom differs only a little bit. Right, so the hom phi of hg is some value that differs from the target less than the right-hand side. Right, so the right-hand side is epsilon times the product of all these relevant classes times size of h. So when you take the target here minus the right-hand side, you can bring this product outside the brackets, and inside the bracket you just get the product of all the densities here minus epsilon times number of edges of h. Right? So that's just this rephrased, bearing this in mind. And now, let's look what these things are. If we have an epsilon regular partition, well, we're assuming that we have this uniform partition with the various densities. Part of that assumption is that all the partition classes have the same size as they come from the regularity lemma. So this size, call that little l, right? Then these partition classes here all have size L, and this big product that we brought outside the brackets is the product of lots of little L's. How many? Well, one for every vertex of H. So this product here equals L to the power of H, order H. And what is in the brackets now, the difference between the product of all the densities and epsilon times the number of edges of H, all that is a constant. Because these densities are given. They're fixed from the start. H is fixed from the start. Epsilon is fixed. So all this is some constant. And this L grows with G as long as epsilon is fixed, and the partition comes from the regularity lemma, because the number of classes is bounded by big M, so the size L of classes grows with little n, the order of G. So C times L to the power of H goes to infinity with n if the constant is positive. Right? And we don't know whether the constant is positive, but if we assume that, then we'll have this. Okay. Questions about this? Okay, then I have a question. A mean question, as usual. So, if C is positive, if this constant, that is the product of all the densities, if the densities are all positive, which we can assume, that's going to be positive. And now we can make epsilon really, really small, so that the product of the densities minus epsilon times the number of edges of H is positive. And then apply the regularity lemma. And that will return some big M, so that for all graphs that have size at least little m, they have such a partition. But if this C is positive, then C times L to the power of H is also positive, but maybe less than 1. But the assertion is that the number of homomorphisms is bigger than this positive little number. So it seems we've proved that H is a subgraph of G. Any H. I can't be right. Okay, if G has at least as many vertices as H does, right, which we need when we feed the regularity lemma, we have to specify a little m, and we can choose m to be the order of H at least. But then it seems we have proved that H is a subgraph of G, or at least that there exists a homomorphism. We'll have to see whether that's an injective one or not, but at least we seem to have proved that there exists a homomorphism. It can't be true. Or can it be true? So what's wrong? Yeah?
I don't understand how your DEIs are not dependent on G.
Yeah. Yes, I think you're getting to the point there. So we're assuming that G comes with an epsilon regular or epsilon uniform partition with these densities, Dij. Now, that's not something you can assume. So when you feed an arbitrary graph to the regularity lemma, it will return some epsilon regular or epsilon uniform partition, but it will choose its own densities. And in particular, if your G doesn't have enough edges, it could be that all the edges it has hide in a few epsilon regular pairs, for example, by putting all edges, whoops, here. I mean, here's the epsilon regular partition, as you can still see it. If we make this density Dij 1, right, if we put all these edges there, then we can hide a lot of edges for G in few of these pairs, maybe fewer than R has edges. And maybe H cannot be embedded there because we don't have enough pairs, right? That's indeed where the argument breaks down, and luckily it breaks down, otherwise we'd have a big problem. Okay, so the typical application, as I said, is that there are many homomorphisms from H to G that respect phi, many phi-partite ones. And now what we would like is, what we often would like, is a particular subgraph H in G. And there we have a problem. So let me write this on the board. So to show that a given H occurs as a subgraph in G, we need an injective homomorphism of phi to G. Right, then the image will be a subgraph isomorphic to H, and that's what we want. So do we have enough homomorphisms so that if we discount all the non-injective ones, we still have one? So let's calculate that in a simple example. So for example, let all the Dijs be the same. They're all the same D, and let's assume that R is, again, a complete graph, KK. So which H can we find? Well, we want to be phi-partite, so then there's a homomorphism phi from H to R if well, we had that before. If the chromatic number of H is a MSK. Right? If it is, we just map the color classes to one vertex. Every color class gets mapped to a vertex of R, and adjacent vertices get mapped to different color classes. So that's fine. Right? If and only if. So a graph H has a homomorphism to KK if and only if H can be colored by MSK colors, vertex colored, right? So that's just a way of rephrasing chromatic number. Right, and now the counting lemma tells us how many phi-partite homomorphisms there are. Counting lemma hom phi of Hg is at least, now let's look again. Let me just do the big bracket. So the product of all the densities, all the densities are now the same, right? They're all D. So that's the product of all the densities is D to the number of edges of H. Right? That's as how many pairs we need for densities minus epsilon H. So this is just copied from the application of the counting lemma there, and that has to be multiplied now by what? By the product of all these classes. All the classes have the same size. They're all L. How many classes are there? As many as H has vertices. So L times H. Okay. So this is how many homomorphisms we have. Right? But how many of those are non-injective? Non-injective homs. Well, how do you get a non-injective homomorphism? It's non-injective when two vertices of H get mapped to the same vertex of G. Right? How many maps are there? Well, once you have identified two vertices that have to map to the same vertex of G, you have to make order H minus 1 many choices for the vertices that you have, and each image is chosen from a class of size L. So this is the number of maps, homomorphism or not. This is the number of maps in which you can map the vertices of H to their designated classes, each of size L, on the assumption that some two vertices get mapped to the same image. And how many ways are there of choosing those two vertices that witness the non-injectivity? Well, let's be generous. just say just choose a pair, right? Okay, now, this exponent is smaller than that exponent. So when G becomes large, and therefore this L becomes large, then this outgrows that, no matter what the constants are. So as G grows, we'll certainly have some injective homomorphisms left from our count of all the homomorphisms, because there are not enough non-injective ones. And of course, our aim was to find a copy of H and G, and that's what injective homomorphisms do. Proof of the counting lemma. Induction on the number of edges of H as announced, and that's why the nasty little factor comes on the right-hand side. So what about the induction start? We start at 0 when H has no edges. Is that okay? Well, the right-hand side is 0, so we better get 0 on the left. Because there's an absolute value here, so it can't get lower than 0. But we do get 0. Why? Because when you don't have any edges, then all the ways you map the vertices to the correct classes will be a homomorphism. Right? So the number of homomorphisms here will equal the second product here, the number of ways in which we can choose images for the vertices. Except there's this factor there. That's the product over all edges of H, of which there aren't any. And now a convenient assumption that we always make is that products over the empty set are 1, just as sums over the empty set are 0. All right, so with this convention in place, that is at 1, then these two quantities are the same, so we really get 0, and the induction starts. Okay, for the induction step, now it gets interesting. For the induction step, we choose an edge, AB, and of H, and then we want to use the induction hypothesis. So we delete the edge AB. We don't delete the vertices A and B, just the edge, right? And then the homomorphisms we want to count from H to G are a subset of those that we know. This is the same phi that also works on the vertices of H prime, right? Why? Because a map that is a homomorphism from H to G that respects phi is certainly also one from H prime to G. It just has to achieve less. It has to preserve adjacencies, and it has to preserve one less adjacency, right? That between A and B. So we're asking less here, and conversely, whenever we have a homomorphism there, that maps adjacent vertices to adjacent vertices. Is that a homomorphism here? Well, if and only if it happens to map A and B to adjacent vertices of G. It doesn't have to, because in H prime they're not adjacent, but we can just count those separately. We can count the good ones. The good ones here are those we want, and then there are some bad ones that map A and B to non-adjacent vertices. And we have to estimate how many there are, but the induction hypothesis will tell us how many of these things there are, and that's how we're going to use it, induction hypothesis. Right? That's the idea. So let's rewrite the number of phi-partite homomorphisms from H to G in a strange way. This sum here sums over all the homomorphisms from H prime to G. We consider all those, and then we want to count 1 for the good ones and 0 for the bad ones. And that's what this function does here. This is the indicator function for the image under this psi. We're summing over all the little psis in here, and then we look at psi of A and psi of B. And we count 1 if psi of A and psi of B happen to be an edge of G. That's the definition of this funny indicator function here. This is a function on the pairs of vertices of G, and it assigns to a pair the value 1 when these vertices are adjacent and 0 otherwise. Right? And now we're going through all the homomorphisms in our bigger set here, and we count 1 for some of them and 0 for others. And when do we count 1? When they do the right thing, when they're good. So let me just draw a picture of you for this function. One G of psi of A and psi of B. So we have A and B in H. And the various psis, homomorphisms from H prime, so H minus that edge, to G, they can do various things with these two vertices. For example, they could map them to the same vertex. So such a thing would get 0 in this count here. So for this psi, this is going to be 0. Another psi, so this is psi 1, this is psi 2, might map these to non-adjacent vertices there. That also gets a 0. But if they get mapped, if this psi here maps A and B to adjacent vertices, then we count a 1 here. All right, so that's for every little psi, we get one number, either 0 or 1, under that sum. Now, we want to apply the induction hypothesis. And in order to do that, we'll rewrite this sum with a funny statement here with the indicator function 1 in a strange way. And you'll see later why. I don't want to motivate it now and get carried away. Let's just do it mechanically and then see what happens. So first, we subtract this little number d to the phi ab, and we add it again. Right? We're not changing anything. What's that number? This is the density, the target density assigned to phi of A, comma, phi of B. Right? Phi of A is the index of a class, vertex of R. Phi of B is the index of a class, another vertex of R. And this pair of vertex classes comes with a density called d phi of A, phi of B. And I abbreviated that d of phi of A, phi of B as d up phi AB. Okay, this little one, this number, there's just one number. We subtract and then we add it again so that we don't change anything. And now we split this, we rewrite this extended sum by lumping the minus d phi AB together with this funny number, with this funny indicator function 1, and taking the plus phi AB out. So here, the left summand, which is the sum over all size, the phi-partite homomorphisms from H prime to G, the left summand sums all those indicator function minus d phi AB. And those summands there, all these little differences between 1 of blah and d phi AB, all these depend on the particular psi, right? And then the other one, the plus d phi AB, that we took out, well, we just count 1 for every homomorphism, phi-partite homomorphism from H prime to G. Right here, for every psi, we count 1 of those. So we can write this count. For every psi, we count 1 copy of the number d phi AB, and then we get this summand here, d phi AB times the number of these homomorphisms. Why is that a good idea? Because we know this number. This number comes with the induction hypothesis. And there's something even better. Let's look at what we're trying to prove. We're trying to prove that the number of homomorphisms phi-partite from H to G differs from its target, the product of two big products, by a little bit. Now, by induction, we know that for H prime. Now, let's compare the two targets. The target for H prime is also one such big product. And how does that differ from the product for H? Well, the product of all the class sizes is the same, the big pi there. Only the big pi on the left is slightly different because there's one fewer factor. It's a product over all the edges of the graph, which is now H prime, of the numbers d up phi that edge. So this product here differs for H prime, and it differs precisely by the factor that we have written in front of it. That's missing. That's the missing factor from the target value for the HOMS HG. When we look at the target value for the HOMS H prime G. The target values differ by this little factor d to the phi AB that is written here in front of that HOM. So this summand here, d phi AB times this HOM, is close to the target for HOM HG because this HOM H prime G that is contained in there is close to its target by induction. So all we need to show is that this other big summand, the one with the big sum sign here that you can see in the brackets, that this is small enough to be tucked away in the little difference that we still have spare. And what is that little difference? Epsilon times product of the factors. This is what we have to show next. And to prove that assertion star, we're looking at H prime in which we also deleted the vertices. So H double prime is H minus vertex A minus vertex B. So we have to estimate this big sum here, and the sum goes over all the psi's that are homomorphisms in here. It goes over all these elements here, and then it looks at the good ones and the bad ones. And every such psi we now take in two steps. Given a homomorphism psi from H prime to G, we first apply it to all the vertices that are neither A nor B. Okay? Let's call those psi prime. We're summing over all the psi prime homomorphisms from H double prime to G. And then we look which of those extend to a homomorphism of H prime to G. First, we map all the other vertices other than H and B, A and B, to G, and then we see how can we extend that to get the homomorphism from H prime to G that this sum is all about. Right, that's what this line does. And here we have just an application of the triangle inequality that we can move these absolute value brackets inside this sum. But what remains is the same. We've summed first over all the homomorphisms psi prime from H double prime to G. And then for each of those, we estimate the number of ways in which it extends to a homomorphism from H prime to G. And that is, for all those extensions, we have to then count this number. Don't ask what the number is, it's just copied from earlier. Point is that we have to sum over all these extensions. And that's easy to describe because what does such an extension have to do? Suppose we have A and B, and we have embedded all the other vertices already. So we've embedded those, and we have embedded, in particular, the neighbors of A and B. Now, that's a psi prime. Does that extend to a homomorphism psi of H prime? Well, it has to map A to something that is adjacent to all the images of its neighbors. Right? Otherwise, it can't be a homomorphism of H prime. But there may be many such things. So we may have a choice. And let's call the set of vertices from which we can choose those that are adjacent to the images of the neighbors of A in G and lie in the right class, in the target class for little a under phi. Let's call that set WA. And similarly, B has to map to vertices that have the right neighbors. But there may be several, and let's call the set of all those WB. And then the sum that we had up there is over all the choices of a vertex in WA and a vertex in WB. And what do we sum? Well, the values was this one indicator function of psi A and psi B, and that is one if and only if these things are adjacent. Some of these are edges of G, some are not. So the number of those edges is WA, WB. And now we use the epsilon uniformity of this pair of classes, V phi of A and V phi of B, which says, which estimates precisely how much the number of edges between these two sets here differs from the potential number order WA times order WB weighted with the factor d phi AB. And it says that this difference is small, namely epsilon times now the order of this times the order of that, rather than this and that, as in the definition of epsilon regularity. Okay.